So welcome to another in OpenEye Cadence Molecular Sciences series of webinars. Today, our title is Rapid Comparison of Binding Sites with SiteHopper. Today's webinar is going to be given by Callie Burley, one of our application scientists on the West Coast. Callie was a graduate student with David Mobley. She went into industry, first with Vertex, subsequently with Neomorph, joined OpenEye quite recently, and has been focusing mostly on profiling and comparison of protein binding site properties. So without further ado, I'm going to turn it over to Callie for the presentation.
Thank you, Paul, for that introduction. So again, my name is Callie Burley. I'm really excited. It's my pleasure today to present to you on our tool, SiteHopper. I'm going to go over how we use this tool to compare binding sites. So just a brief overview of today's agenda. So I'll introduce why one would want to align and compare binding sites, how we actually perform this comparison with SiteHopper, how well does the SiteHopper application perform? If you want to run your own SiteHopper queries, how are the patch databases that you query against generated? And how do you, practically speaking, use SiteHopper? So starting with our first bullet point here, why align and compare binding sites? Well, there's a number of reasons that you might want to do this. So let's start with the case that you're working on a particular target and you have multiple structures of this target, or there are other publicly available structures of this target where it's bound to different ligands. And perhaps in the case, for example, of this one on the right, there's some sort of conformational change that occurs, or maybe there isn't. Either way, we ultimately want to see the overlay of these two pockets so that we can better interpret our SAR. So here, SiteHopper can be used to align these pockets with these different ligands. Another reason you might want to align and compare binding sites would be if you are working on a particular project and you are concerned about selectivity. So perhaps you have a similar related protein and you'd like to align it with your target protein so that you have a better sense of where you might be able to gain selectivity. So that would be another reason to use SiteHopper. Another interesting application of SiteHopper would be to try to identify pockets with similarity to your target pocket so that you could ID potential ways of repurposing your drug. For example, what other compounds or pockets might your ligand bind to? Or from the case of a liability, you might be able to identify potential off targets that you might want to have in mind as you optimize your ligand. Additionally, if you're starting just with a pocket itself, you might use SiteHopper to identify a tool compound. So say I have an APO pocket, I could run against a query set of liganded pockets and potentially identify tool compounds that might bind my pocket of interest. So how can we compare binding sites? So one might use sequence alignment as a way to compare binding sites. So here I'm showing you the example of carbonic anhydrase 1 and carbonic anhydrase 2. You can see that they overlay nicely. And in fact, these two proteins share a common ligand, highlighted here in purple. If we look at the sequence similarity and identity of these two targets, you'll see that they have relatively high identity and similarity at 61% and 73%. So in this case, using a sequence-based method would be a good way of identifying this pair of proteins. Alternatively, let's take the case of Wee kinase, shown here in purple, and TNIC kinase, overlaid here. These two proteins also share a common ligand. However, if we look at the sequence similarity and identity between these two systems, you'll see that it's much lower, in the range of 20% for sequence identity and 40% for sequence similarity. So for this particular set, a method such as a sequence-based method would not work so well to identify these two pairs. So can we do better than sequence alignment? This is a question that we've addressed in ways before here at OpenEye. So OpenEye, we really believe that there are two fundamental properties that describe molecules. You have the shape of the molecule as well as the electrostatic features of the molecule. And if you can describe a molecule by its shape in electrostatics, you can understand the bioactivity of that molecule. So molecules with similar shape in electrostatics are expected to have similar potency, selectivity, and probably pharmacology. So these two principles have been employed very effectively in our tool ROCS, which is our ligand similarity search tool. And in ROCS, what we're doing is we're taking the representation of our molecule and we're recasting it as a representation where we include the shape as well as colorimetric features to describe or as a cognate of the electrostatic features of that molecule. And using this approach, we've been able to very effectively and efficiently identify compounds that have dissimilar 2D path similarity, but can have very similar 3D similarity. And this tool has been incredibly effective as a ligand-based search tool. So taking these same principles, we've gone ahead and applied a similar method to binding sites. So in the case of SiteHopper, what we're doing is we're taking a binding site and we were describing it in terms of its shape and its colorimetric features. So how do you define the shape and the color of a binding site? I'm going to walk you through exactly what we do. So the first thing we do is we create a pocket surface around the ligand. So we collect residues within 4 angstroms of our binding pocket ligand and generate a surface. To make the surface, we actually place atoms across the surface of the molecule to make that shape. And then using residue atoms within 4 angstroms of that surface, we define color atoms to describe the different features of the residues in that area. And then we retain the features that are within 1 angstrom of the surface. So what does a SiteHopper search actually look like? So we start with our query patch, that shape and color representation of our binding pocket, which I'm going to represent here in a 2D just to make it easier to see. We take our query patch, and then we also take a database of patches. And I'll speak more about the databases in a little bit. So we overlay our query patch across all of the patches within the database and do a general alignment, and then we optimize that alignment. And finally, we score the alignment, and our score is a range from 0 to 4. If you're familiar with ROCS, ROCS has a score based from 0 to 2, which is a combination of shape Tanimoto and color Tanimoto. Here we are weighting the color Tanimoto score, so we have a range then from 0 to 4. So what kind of output do you get from SiteHopper? So if we were to take this pocket query here in the middle, you'll notice that it has a number of different features, different color features, as well as different shape features, such as this bump. The type of results that we return will actually retain those features. So you'll see many of the color features and the shape features are retained, including that little bump. So when we run a SiteHopper search, we actually end up with the alignments of all of our pockets with each other. And in addition, we end up with the similarity hit list, where the pockets are ranked according to that patch score, that combination of shape and color. In addition to getting the composite score, you also get the component patch scores for each hit. So just to review the overall SiteHopper algorithm as we've moved through it. First, we start with our protein and a binding site. I have the ligand here marked because whether or not there's an actual ligand there is optional. It's optional to define the binding site with a particular ligand. You can also use apo sites. But you start with that binding pocket. We generate a patch from that binding pocket. We align it and optimize that alignment against a number of patches within a query database. And then finally, we score those metrics to get a hit list as well as return the alignment of those different patches binding sites with each other. So how well does this method actually perform against these sequence-based methods? I showed you at the beginning that sequence-based methods can be really effective where there is, high sequence similarity, but there are cases where, or examples where there are targets or binding sites that share a ligand but have low sequence similarity. So fortunately, as this tool was being developed, it was actually validated in collaboration with Vertex. So Vertex curated a set of protein pairs, so a set of what we will call positive protein pairs, and these are pairs of proteins that share a common ligand where the ligand binds both targets at less than 100 nanomolar. At least one ligand binding both targets at less than 100 nanomolar. They also generated a set of negative protein pairs, and these are protein pairs for which there are 3 or more ligands which bind one target with an affinity less than 10 micromolar and one target with an affinity greater than 10 micromolar. And this must occur at least on the order of 3 or more, in 3 or more instances of compounds. So using this curated set, Vertex applied a few different methods, some sequence-based methods, as well as the SiteHopper method that I just introduced. And if we look at the performance of those sequence-based methods, they looked at both overall sequence identity as well as the pocket sequence identity, where you look at, the first residue where the pocket is represented in that primary sequence all the way to the last residue. So looking at the comparison between that linear definition of the protein in that region, as well as just looking at the specific residues that make up the binding pocket. And you can see that if we just look at overall sequence identity, that method doesn't perform particularly well. But if you focus in on pocket residue sequence identity or looking at that sequential sequence from the first pocket residue to the last pocket residue, these methods are fairly effective at identifying positive protein pairs. If we look at the performance of SiteHopper, you can see that it is comparable to these pocket sequence similarity methods. Where SiteHopper really shines, though, this is an overlay here of the different approaches of those AUCs, where we're looking at it compared to pocket residue identity. And what we see SiteHopper here in red is that SiteHopper has an added advantage of really identifying similar protein pockets that share cognate ligands in the case where there is just low pocket residue identity. And the reason we're able to do that is because we're abstracting here with this method from the actual residue identities that make up that pocket. So there's a real advantage that's conferred here by SiteHopper. So coming back to our overall SiteHopper algorithm, one thing that I haven't talked about yet is this patch database. So where do these patch databases come from? And how are they built? So I'm going to walk you through how the patches are generated. So we start by preparing the structures. These can be proprietary internal experimental structures that you have at your company. They can be publicly available structures, such as those deposited in the protein data bank. They can be simulated structures, homology models, frames from MD trajectories, or they could be computationally AI-generated models, for example, from AlphaFold. The next thing you need to do is to identify the pocket. So you can imagine in the case where there's a ligand, this is pretty straightforward. In the case that there aren't ligands, we use OA pocket and F pocket to identify cavities across the surface. And it's these cavities then that go on to define the patches for SiteHopper. So once we have identified those pockets, we generate the patches, and all that data is stored efficiently in a patch database. So we provide a few databases for folks who license this tool. The MMDS, or macromolecular data service set, which is from a curated set of ready-to-use protein models that we've prepared with our tool Spruce. It contains over 197,000 protein ligand binding sites, and these were generated using structures from the protein data bank where there are ligands present. We also offer, if you license our Orion platform, you have access to these alternate sites. And this comprises over 2 million putative binding sites. So these are sites for which there aren't necessarily ligands, but we've used our OE pocket or we've used F pocket to identify potential cavities across the surface that might comprise pockets. So how can you use SiteHopper? There are a number of ways. So you can use SiteHopper as a toolkit. So you can use Python, for example, to write your own scripts, to use SiteHopper to do what you'd like. You can use our desktop application, which with a one-line command, you're able to provide your query, your database, and generate your output. And then we also have our SiteHopper search deployed on Orion as a simple flow that you can run by providing your outputs with a few clicks. One advantage of using Orion is that you have access to our 3D Analyze page. So on the Analyze page, you can actually visualize the alignment of your different binding sites and visualize the patches themselves. You get that hit list in our spreadsheet view of those scores. And you also have the advantage of these interactive 2D plotting. So I want to show you what these results actually look like in Orion and how you can manipulate and review them. In order to do that, we're going to look at a test system. So we're going to run SiteHopper on this human androgen receptor binding site here, and you can see it's bound, in this case, to this androgen receptor modulator. This is a structure from the PDB. So we'll take this pocket and we'll run it in SiteHopper. And now I'm going to show you the results that we get. So you can see there's our query ligand here, binding site with the patch generated. You can manipulate. We have a spreadsheet here, which if we make larger, you can see, as I mentioned, you have the titles here of the different PDB structures, as well as whether there's a ligand present or if it's an apo structure, some definition of where the pocket is located, what residue chain and residue number. You have our component patch scores. You also get this target name. And you can see as we scroll down, there are things that are not androgen receptors, like estrogen receptors, mineral corticoid receptors. You have this plot here. I'm showing a histogram of the patch scores. I can go ahead and add additional plots if I'd like. So I'm just going to toggle on the sequence similarity here on our x-axis, keep our patch score, and then I'm going to color by that target name feature. If I go here and select target name, I'll get this color representation of the different targets. So you can see the targets kind of naturally cluster based on that sequence similarity. So you have the estrogen receptors, alpha and beta. And again, this plot is interactive. So whatever I click here on the left will actually populate here on the right. And if there's a ligand present in that structure, it'll show the overlay of the binding sites with that ligand present as well. And you can manipulate your view here. You'll notice, so like this one that I clicked on is actually an apo structure. And so there's no ligand. So I'm going to actually filter out all the apo structures. I'm only interested in viewing hits for which there is a ligand present. So if I make my 3D viewer large here, I have this overlay and I can just highlight and click through all of these different overlays of binding sites generated from SiteHopper. And you'll see that there are a number of similar sites with interesting diversity in the ligands that are actually present in that site. So you can imagine SiteHopper is a fairly powerful tool for being able to identify potential ligands, for example, tool compound, or to identify potential off targets, looking at those different target families that come up. So coming back to here, let's just review those results. highlight a few of them that we got. So we returned some hits from the human progesterone receptor family. And those hits have pretty high sequence similarity as it is, but look chemically distinct. But you can see with the nice 3D overlays here how there's some similarity there. We also returned the human estrogen receptor alpha and human estrogen receptor beta, and these actually have a bit lower sequence similarity here at 56% and 68%. We actually return, one of the pockets where estrogen is bound, which is similar to the cognate ligand for androgen, which is testosterone. And in fact, we actually return the cytochrome P450 BM3 mutant, which has 54% sequence similarity, and it's bound to our negative ligand here, testosterone. Interestingly, if you look at the source of this particular structure, it comes from this paper where they've used directed evolution to engineer these P450 BM3 mutants to specifically hydroxylate the ligands. In this case, this has been specifically engineered to hydroxylate testosterone. So I found that really interesting that this method is able to pull out engineered binding sites as well. So with that, I'll wrap up. We talked about what SiteHopper is, its genesis and its similarity ROCS. It's really an analogous tool where we're abstracting from the specific atom IDs and we're turning it into a representation of shape and color. We went over the specific SiteHopper algorithm to give you a sense for how it works. We talked about patch databases, which ones we provide, how to generate your own, and then we also looked at how you can review results in Orion and what the results actually look like. So with that, I'd just like to acknowledge my colleagues at OpenEye. There are a number of folks you'll see and hopefully get to interact with as customers. Both, our customers have access to our scientific developers as well as our application scientists. We provide a lot of support, so really take advantage of that if you are or do become a customer. And with that, I know we have some questions coming in. I think we're going to transition now to our Q&A session. If you aren't already, please subscribe to our mailing list. This is a QR code, and you'll get updates about upcoming webinars as well as local events that we host.
So Callie, thank you very much for that. Fascinating as always. A key question when anyone's thinking about comparing binding site patches and so on is, how would I generate a patch database of my own if I want to use structures that have been generated in-house and aren't available publicly?
That's a great question, Paul. So I covered this a little bit in the presentation. Practically speaking, it's actually quite easy. So the first thing you need to do if you're using your internal set of structures would be to prepare them using our Spruce tool, which is a really fast and efficient way to prepare your structures. And then after that, all you need to do is run it through our patch database generator, which again, you can use either via toolkits on Orion or using the desktop application. Just a matter of one line or a few clicks, and it'll automatically generate that patch database for you.
Oh, easy, always good. We like that. So getting a little more sciencey here, the question that came in was about the null model that you used, which was sort of sequence similarity, which is a pretty basic null model to compare a very sophisticated 3D model like SiteHopper to. If you use something a little more sort of structure-driven as a null model, how do you see SiteHopper comparing there? What do you see the advantages and disadvantages would be for things like DDM, for example?
Absolutely. It's a great question. We are using a very, very simple null model here to make our comparison. I would say that I would expect structure-based methods to perform well. Absolutely. I think one advantage of the approach that we take is that when we abstract away from the actual atoms themselves, we get a more generalized picture of the binding pocket and more generalized description of it. And that provides an advantage, I would say, over methods like DDM. It also makes it an extremely fast method as well. to quickly perform those overlays. So I think we really, in terms of how well we compare relative to those methods, I don't think we have those numbers available, but I would expect us to compare to perform comparably. But in this case, I think we do have that advantage of having that total abstraction.
Okay. So you talked a lot about comparing structural models from crystallography or presumably cryo-EM and things like that. But obviously, there are a lot of other places we can get atomic models of protein conformation. And a very popular question coming is about various aspects of molecular dynamics simulation. So does this method apply to coordinates you generate from simulation as well as methods that give you coordinates from experiment?
Absolutely. So it is agnostic to the source of those coordinates. So if you want to, say, run an MD simulation and cluster your frames and select, different representations of your site, this method absolutely supports that. I think one thing that's also nice about this, and this is maybe related to the question you asked about comparing to other structural methods here, is that when we abstract away from the coordinates or the atom IDs, we're actually using a soft Gaussian function to compare the different features. So in a sense, we already have this sort of smoothing feature built in. So the precise location of those atoms in space isn't as critical as it would be for another method.
Okay. So you talked briefly about the way that we're assessing protein pocket similarity using this combination of similarity in shape and similarity in color, where we have a weight toward the color, I think, if I remember rightly. And we're using a Tanimoto coefficient for that. So how did we come up with that scoring approach, and what thoughts do you have on how we might improve that scoring approach in future?
Yeah, it's a question that comes up often because it's, it seems like a general, 3x color is what we do and 1x shape. And this is something that was really uncovered heuristically during the development process of this tool. Certainly there are options as a user to kind of, because you get the return of those component scores, you can actually tweak and try to figure out what final scoring function works well for you. To get to your question about Tanimoto, it's because we're looking at sites that have different sizes. One could hypothesize that maybe that's not the best approach if you're looking at pockets of different size, and so you might be more interested in using an asymmetric method of similarity, such as Tversky, and that's something we are exploring. As it is, the Tanimoto method is a bit more intuitive for users, but certainly we are open and actively, exploring the possibility of using things like Tversky.
Okay. So we think about Tanimoto, perhaps if you're looking for pockets of around the same kind of size as the pocket but maybe Tversky if you're looking for pockets maybe much bigger or smaller even?
That could be possible. We do have a function within our SiteHopper flow where we try to normalize and rescore the overlays based on or accounting for the fact that the pockets can be different sizes. But in terms of robustly addressing the question of whether a Tversky metric would be more favorable than a Tanimoto metric in your final output, that's not something we have direct data for yet.
Some future science to do.
Absolutely, always.
And quite a detailed question. In the validation study from Vertex, they were reporting generating a negative and a positive set by looking at the ligand affinities, and where the positive set was using high affinity ligands and the negative set was using low affinity ligands. A question came in about whether using low affinity ligands really gives you a negative set of pockets, because the ligand actually does bind to the pocket even though weakly.
Yes, good question. It's really a tough problem to be able to identify true negative protein pairs. I don't know if you noticed, but on the slide I had annotated how many sets of pairs they had for positive protein pairs versus the negative protein pairs. For the positives, it was over 6,000. For the negative protein pairs, it was in the range of 300 to 400. Yes, so it's much smaller. So already setting those constraints of having, activity greater than 10 micromolar as the bottom there, has already cut down the number of pairs for which to perform the validation. So I think you're, up against that challenge. Ideally, you would have a set of negative protein pairs for which there is no measurable activity of that ligand on one of your targets. But unfortunately, that's just the limits that we're up against. It's definitely an imperfect experiment, but I think still a nice data set for validation.
Yes, in the Google limit, we'd have all the data we need, but we have to use the data we have.
Exactly. Ideally, you'd have that measurement for everything, and you could pick and choose, and go beyond, that set of 300 that we currently have.
Well, that's all the questions that have come in for now. So, Callie, I thank you once again for that. That was really interesting. And we look forward to having all of you come back and join us for the next webinar in our series. And so in the meantime, thanks for coming, and we'll see you next time. Goodbye.